Welcome everyone to our sixth and final lecture on large language models. So large language models have become very popular, especially with the rise of ChatGPT and things of that nature. I'm really excited to talk about large language models and how to integrate into the things we've been learning for the rest of the lectures before. So tonight's learning objectives, first we'll talk about the final project. Second, we'll talk about sort of the paradigm behind how these large language models are trained, which is pre-training and fine-tuning. Third, we'll talk about what language modeling actually is. Fourth, we'll talk about how we can align large language models to human values. And fifth, we'll have a code demo on building applications using large language models. So I'm really excited about today's lecture. And without further ado, let's get started. So first, the final project. So this is something we do every year in the AI camp. And this year especially, I think it'll become a lot more approachable to actually build something using a lot of the stuff that we learned in the camp, and then put that and use that to benefit your community. So the idea behind our final project is to use what you learned in the camp to come up with a project idea of some project that you think can help your community or your environment. So what we recommend is look around you and look at the problems that your community is facing, and then think about ways that you can apply things that you learned in this camp or just AI more generally to help solve those problems. So in more specific detail as to what we want for the final project, what we expect is an abstract or a summary of 200 words. In addition, we would like a 2-minute video which explains what this project will do, how this project will help the community and the environment, and how you can actually implement the project. And here, please use a concept that you learned in the AI camp. In addition, something that we do not require but recommend is a prototype or code, sort of just implementing what your project does, and just showing some code snippets of that. So you can explain that in a video of up to 3 minutes, and this can be an additional video on top of the 2-minute video. And we'll look over your projects, and the top projects will be featured on our website, which is the communityai.org. Our final projects are due on 12th of July, 2023, and they must be submitted on time in order to get the certificate. And at the end of the lecture, we will have, so Shroman will talk a bit more about the logistics behind the final projects. And at that time, you can ask us any questions that you guys may have about the final project, or you can also post in the Google Classroom and we'll answer as soon as we can. So let's get started on large language modeling. So what is a large language model? So the idea that you can maybe think about is something like ChatGPT. The idea here behind what we're sort of trying to build is a thing where you can ask it questions and they can answer in a human understandable format. And to do so, the biggest thing that has worked very well is pre-training and fine-tuning. And so first, let's discuss this paradigm. So the idea behind developing something like ChatGPT is first having a neural network that understands many general things about the world. And this is called pre-training. So during the pre-training process, for example, the model can understand, maybe learn grammar, it can learn things like what countries are, what states are, what are some popular books. You can learn maybe some things about math, about logic, maybe even a bit things about coding and so forth. And in terms of a nice analogy that Dr. Buller came up with, and I think it's great, is that this is really like high or secondary school. So the idea here is that you take a wide variety of classes, and that increases your general knowledge about the subject. And then this can serve as sort of a base into learning more advanced things. And in terms of learning more advanced things, in terms of our paradigm, that is called fine-tuning. So now that we have our pre-trained model, we understand a lot of general things, we now will fine-tune it to a task that we actually want our model to do well on. So for example, question answering. And in terms of a real life analogy, this can be like attending a university. So in high school, you sort of had a general knowledge of a lot of different things. And now in university, you're going and getting a specialized knowledge of some topic. So say you go and study computer science, then you will learn a specialized knowledge in computer science. But the things you learned in high school will serve as a important baseline knowledge towards actually understand computer science. And so that's sort of how you can think about pre-training and fine-tuning. In terms of how this happens, I guess more concretely, you first train a neural network, and similar to how we talked about last lecture, so with regard to back propagation, forward propagation, and so forth. So you train this neural network to understand a lot of general things. And when fine-tuning, so the idea is that you start with the same weights or parameters that you started from in pre-training, and then you build on top of it to do well on a fine-tuned task that you want your model to do well on. So for example, question answering, maybe coding, math, whatever. So the first question that you guys may be asking is, well, this sort of paradigm makes sense, but how exactly will this work? And so let's think about how we can pre-train. And when we pre-train, we do something called language modeling to pre-train. And this is sort of where the name large language models or LLMs come from. So language modeling is a task of predicting the next word given a series of prior words before it. So for example, if you have the sentence, which is once upon a time, Dash lived a sleepy rabbit, you would fill this in with there. And this is what language modeling really is, where you're sort of trying to fill in the blank based upon prior words that you have. Mathematically, what we can think about is predicting the probability distribution of the next word. So the idea here is that, let's say you have your previous tokens, x of t minus 1, t minus 2, or 2x of 1, which in this example would be maybe something like once upon a time. So that would be these values. And your goal is to predict this value. So the idea here is that your goal is to predict the probability distribution of the next word. So maybe something, one simple example could be the word THEIR with probability 0.6, the word THERE with probability 0.1, the word rabbit or something with probability 0.15, and so on and so forth. And in terms of how this would work in test or inference time, we would just see generally which word has the highest probability and just place that in, and that will be our prediction. And so that is language modeling, and that is how we pre-train these models. But one question that you guys may have is, well, why language modeling? Why does language modeling help solve this task of pre-training, which we define as, understanding many general things about the world? And these are the two main reasons why. Sorry?
Hey, so I noticed it, and someone else just mentioned it too. There's like a gray box on the lower right corner of the screen.
Is that visible?
Yeah, it's visible.
Okay, let me try and do a new share. Give me a second. Let me just unshare my screen.
Sorry, I didn't want to interrupt, but
okay, no problem at all.
I've noticed it too.
I'm just closing a lot of my tabs that I have. I'm not sure where this gray box is coming from. I think the best solution might be just I'll just quickly restart my computer and come back in. So I'll quickly leave my thing here and I'll join the Zoom.
Here, let's avoid that for now.
Okay.
Let's just try resharing and see if there's some kind of like preview screen or something.
Okay, let me see. Give me 1 second because I closed that tab.
Or if not, you can restart while I'm doing my part of the lecture.
Oh, that sounds good. Yeah, I'll do that. Just give me a second. Let me just open this and just like share this part. How about now? Does it still show?
Doesn't look like it.
Okay, great. So when I was sharing, like could people just not see certain information?
Yeah, it was on the bottom right, but I think it
Okay, just like this stuff.
okay.
Okay, sounds good. Like, would anyone like me to repeat anything, or do you think it's fine?
I think it's good. People will have an opportunity to see the slides afterwards.
Okay, sounds great. Awesome. So where I was at is why language model. So just to sort of summarize what I talked about the last minute, is we have language modeling, which is how we pre-train these models. But how exactly does language modeling correlate with pre-training? Because what pre-training was a neural network that understands many general things about the world. So how does language modeling help understand these general things about the world? And the reason that we do this is twofold. First is that there's a broad availability of data that can help with language modeling in the English language. Because sort of, if you think about what data we really need for language modeling, it's just a series of text, right? Because say, think about a textbook. That can be a huge source of information for language modeling because that has a lot of structured text, right? In like a sentence format. And then you can easily predict the next tokens using the previous information. And you have a huge abundance of that data in the English language. I will say though that there is a large issue with this in other languages. So for example, in the English language, in say English language Wikipedia, there's lots and lots of different Wikipedia pages that you can use to say train your model on. For many other languages, there just aren't that many. And it's this almost ongoing research problem to try to figure out how you can pre-train or how you can even do language modeling with these lower volumes of data, because this volume of data is simply not available in other languages. But with that being said, this broad availability of data is one reason why language modeling is so good. And the second reason is that to really become good at this task of language modeling, at this task of predicting this missing token, the language model really needs to learn a huge amount of things about the world, about English syntax, and so forth. And for this, let's give three sample examples in a data set that we may use for language modeling. First is say something like this, the first sentence. Harry Potter and the Sorcerers. The answer is stone. And to understand, for a language model to get this correct, the language model needs to know a lot of things about books. So this is a book, right? And so in order to answer this, the model needs to learn about literature, different kinds of books, and so forth, especially modern books. Second, one way to optimize a loss function is dash descent. The answer here is gradient descent. And in order to understand this, the machine learning model, the language model, really needs to understand something about machine learning, right? That or else it just wouldn't be able to answer this question. Third is this one. The man won the race. Dash is very fast. The answer is he. And to do this, the model has to really understand a large amount of English syntax and grammar. First, it has to understand that we're referring to the man here, right? That this is a pronoun that we're referring to the man. And second, the model has to understand that in English language, when a masculine person is referred to, then we use the pronoun he instead of she or any other pronouns. So that I hopefully convinces you how language modeling is directly tied to understanding many general things about the world, and thus is an effective task for our model to do pre-training. And as an example of a pre-trained model, one that comes to mind and one that is very popular is called BERT, or bidirectional encoder representation from transformers. And this model was developed by the company Google, and it really the main thing here is that it's bidirectional, meaning that the model here has access to the context words both before it and after it. So, for example, in this case, the model would have access to both the word descent and the words one way to optimize the loss function is. And some people may wonder what this word transformers means. And the word transformers here refers to the type of neural network that we're trying to use. So this type of neural network architecture has been very, very effective and works really well in these tasks. And that's actually mostly what's used in these kind of tasks. And ChatGPT, for example, likely uses transformers as well. And we won't go into what transformers actually are in any detail, but as a quick summary, transformers use this thing called self-attention, which is the main part of it, the art of transformers. And the idea behind self-attention is that we sort of focus on one part of the input. So just as we as humans say when we're reading something or when we're trying to translate something, we focus on one specific part of the input. And this is sort of analogous to what attention is. And that's the core block behind transformers, the core building block. And again, we won't go into this at all, but there's a lot of articles these days about transformers. And if you're interested, let us know, and we can maybe talk about that in the Google Classroom. Or, there's many articles about it online, and I'll highly encourage for those of you guys interested to go and learn more about that. So going back to BERT, so it's bidirectional encoded representation from transformers. So bidirectional, we again said, is when we have access to context words both before it and after it. And that's and this is what our sort of scenario is in doing language modeling. But one quick problem that you guys may recognize is, well, if you have access to all the words before and after, then this creates a problem in our language modeling task, because the model can simply just look up what the next word is and just not learn anything because we have access to all the words after as well. And this may mean that, well, the model isn't learning anything at all. It's just learning to look at the next word. But in a real world case, you won't have access to the next word. And so this becomes pretty pointless because your pre-trained model isn't actually learning anything. How do you solve this problem? The way you solve this problem is something called masked language modeling. So the idea here is that you randomly choose words to mask out, and then you predict the masked out token. So going back to say this example, you would say masked out. Say you have the entire sentence in your data set called one way to optimize the loss function is gradient descent. So you have the sentence. And say you mask out the words optimize and descent. And then you have your model predict this word and this word. And now it turns out that in the BERT paper, it didn't actually do this masking for every single case. And the reason is that you sort of don't want the model because in a real world case, when testing, you may actually have access to these words, right? In a real world case, you won't always have these words masked out. And so for a very small portion of the data, you actually have the whole thing. The one way to optimize the loss function is gradient descent. And you predict it as well. But that's just a minor detail of this BERT paper, just to make the pre-training model work well. So math language modeling is the answer to our problems. Now, after BERT was released, something called RoBERTa was released. And many actually other models that built upon BERT were also released, but this, I would say, is the most prominent and well-used even today. And so what BERT, what RoBERTa really did was it took BERT, but trained it on a huger data set, a much bigger data set, and also trained across more epochs. And they also, did some minor changes to the training methods, but that wasn't really the big picture. The big picture was that it just trained it on much larger data sets and on much more epochs. And that made the model a good bit better than BERT. And RoBERTa is completely open source, and it's actually a very good choice to use in a real world project. And this is a link to RoBERTa. And we highly actually recommend using this maybe in your final project for the AI Cam. So that's what I have on my part. Now, Dr. Willard will talk to us about aligning these language models that we talked about, the human values, and on some practical details about language modeling. Dr. Willard?
All right, thank you, Shreyas. So let me share my screen now. All right, and is that visible for everyone? Great. So as Shreyas was mentioning, these models are trained by basically allowing them to study large sets of text often scraped from the internet. And, basically all it's doing in a simplified sense is finding probability distributions, which basically say, I expect to find this word next to these words, which is great. It's very powerful. But these large language models don't really have a lot of direction beyond that. And so here's an example of one way in which things can go wrong. So if you were to prompt GPT-3 and just ask, what is linear regression? You might get this blurb of text below. Output 3, interpretation of output figure 12.7 from the production prediction of manufacturing. 1, multiple linear regression. So what is it doing? Is it wrong? Well, it's kind of a tough question to answer. What it's doing is it's predicting the next most probable word as it goes along and continues to output text. And so maybe what it's found here is from a statistics textbook or a machine learning textbook, and it's referencing images from that textbook or figures. So that's not really what we wanted it to do. It doesn't mean that GPT-3 isn't useful, because we know very well that it is. But it means that we need to find a way to align these probability distributions with human values. And so the solution here is called instruction fine-tuning. And so we're going to start with the weights from this pre-training. Basically, the pre-training, again, is just a language model looking at tons and tons of texts, books, articles on the web, etc. And then we're going to train it on a large amount of tasks that are actually aligned with human values, such as question answering, detecting toxic language, etc. And where these kind of outputs have been given by a human or labeled by a human. So here is an example from a paper that was published last year, where many of these common fine-tuning tasks have been described. So these are all pretty cool. I won't go into all of them. There's something on the left side called extractive QA, or extractive question answering, where basically you give the large language model a section of text, maybe a paragraph from a news article, and then ask it a question, ask it to extract something of interest from that article. There's topic classification. So if you had a large number of documents, you might want to assign each one of those documents a topic. In the light purple region in the bottom is some very cool fine-tuning tasks. One of these is like arithmetic reasoning. So these models have been shown to, given a few examples, be really, really good at kind of this chain of thought. That's what that COT represents. They're able to kind of reason and kind of follow a sequence of logic. And then, you see some more here on the right, like I mentioned before, toxic language detection, being able to identify when someone's saying something that's not very friendly that you might want to censor from your website, or kind of other tools that you might use. And so these models can be given a lot of examples for any of these tasks, and then we further tune or train the model that had been previously pre-trained to get really good at doing these tasks that are of greater human value. One solution, which was responsible in many ways for the breakthrough of ChatGPT, is this concept of reinforcement learning with human feedback. So this is unfortunately a really short course, and we only have time for 6 lectures. But if we had time for more, I would have loved to spend one of the lectures just talking about reinforcement learning, because it's a really cool technology that I mentioned, I think, in the first lecture. But basically, reinforcement learning is about training bots or agents to make optimal decisions given a scenario. And it turns out that this can be applied to large language models as well, where a human essentially grades the answers that the large language model is providing. So when ChatGPT was developed, this task or this technology, RLHF, was used to basically continue to fine-tune the model to give answers that people preferred. So as it notes at the bottom of the slide, RLHF is very expensive because we need humans to label outputs. One way this might work, the large language model might propose 4 different answers to the same question, and the human annotator would read all of those and rank them in order of their preference. After the humans have done that, we use this reinforcement learning technique to learn a reward model based on how much it expects people to like a response. So more or less, it'll get more points or more reward for creating responses that are expected to align with what humans value, and fewer rewards for responses that humans won't like. And so once we've kind of gotten it started by hand labeling some of these responses, the RL agent learns this model of human preference and can continue to fine-tune itself or fine-tune the large language model by trying to maximize reward. Very cool. In reality, it's not an overly complicated concept, but requires a lot of, very sophisticated algorithms. Another component of this fine-tuning is something called parameter-efficient fine-tuning, or PEFT. So let's maybe just take a moment and pause. In lecture 5 on Monday, I talked about neural networks and how big some of these neural networks get. So when we did our lecture 2 and 3 on linear regression and logistic regression, we often had 3 or 4 parameters or weights that we were trying to optimize. In the neural network lecture, I think at one point I was training a model that had up to about 500,000 parameters. In the large language model world, 500,000 parameters would be very, very, very small. BERT, the model that Shreyas mentioned a few minutes ago, had 340 million parameters. So let that sink in. That's 700 times larger than that neural network that we were training. I might have even forgotten a digit there. Either way, very, very, very large. And the models that are being created today are generally even bigger. GPT-3, which is what enabled ChatGPT and has kind of set a standard for much of the work being done today, is 170 billion parameters, billion with a B, or 170 followed by 9 zeros. So it's just amazing how massive these models have become. And for that reason, most people, or even most businesses, don't have the resources to fully train one of these models or even fine tune one of these models if they were going to tune every single variable in the model. So one thing we do is when we're fine tuning, maybe for a specific application, like for example, let's just say I work in the energy industry, which is true, but maybe these models don't do a good job of understanding energy industry specific lingo or terminology that we use all the time, or maybe they have different meanings in general English and in the energy industry. And I might want to fine tune a model so that already knows English very well. I don't need to start from scratch, but I could take a model like BERT or Roberta or even GPT-3 and fine tune it for my own purposes by feeding it lots and lots of documents in the energy industry. But again, that could be really expensive because these models could have 170 billion parameters or more. So we choose to only fine tune a very small number of parameters. Going back to the kind of idea that Shreyas mentioned earlier about, pre-training is kind of like high school and fine-tuning is kind of like college. You don't need to learn everything from scratch when you're in college. When you're taking your calculus course, you don't have to relearn algebra and geometry. You just kind of learn more things at the edges. And that's the same premise here with parameter efficient fine tuning. We can tune just the parameters at the beginning of the neural network, at the end of the neural network, or possibly even add on a couple layers at the end of the neural network. But we don't need to tune the whole thing, which is a really great thing that we've learned related to transfer learning. And we just want to adjust a small fraction of the number of weights, which makes this a much more tractable problem for your everyday practitioners. This is a really cool idea as well, and something I mentioned a few slides back. There are some emergent properties of large language models that we didn't really expect. And one of these is called in-context learning, where the model can perform better than expected by conditioning the LLM on some input-output examples. So here, we didn't train the model specifically to solve number puzzles, where 1 gets mapped to 1, 2 gets mapped to 3, 3 gets mapped to 7, and then ask it, what does 4 get mapped to? But it turns out that these models are still pretty good at solving problems like this, despite it not actually being trained. So while we can't talk nearly about everything that we want to in large language models, I would highly recommend learning a little bit about this if you have some free time and want to read. In-context learning is very interesting. And I would also encourage you to look at things like few-shot prompting or single-shot prompting, in which your prompt to the large language model contains some examples of the way in which you want it to respond or want it to think. This is related to the chain of thought reasoning I mentioned a few minutes ago. So all in all, we still as humans haven't scratched the surface of what these large language models will eventually be able to do, but they're already showing amazing promise and are doing things that we didn't even necessarily train them to do. So with that, I've actually finished the slides for this evening, and Shreyas will jump in and do a bit of a code demo.
Can everyone hear me okay?
I can.
Yeah, just making sure. If you give me a second, let me share my screen. Is the thing still visible, like as in the gray box, or is it gone?
It's gone.
Okay, great. So welcome to the code demo portion of this lecture. And what we'll do is threefold. The first, we'll show how LLM without instruction tuning or RLHF works and how and sort of how well it does. Second, we'll talk about a model which has RLHF and a lot of instruction tuning done on it, which is the OpenAI's ChatGPT model, called GPT 3.5. So we'll show how you can get that working. And third, we'll show how you can fine-tune OpenAI model, specifically how you can fine-tune GPT-3, and we'll show you how you can maybe construct a data set, and so forth. So let's get started. So first, what I'll do is I will mount my Google Drive. So this is so I can access files on the Google Drive. So I'll first on that. I believe I already did that, but it is great. Yeah. So I already mounted my Google Drive right before this lecture. But if you haven't, it'll sort of tell you to just log in if you're using your email account, your Gmail account, and this will give your Colab access to your Google Drive. Then we will install the OpenAI library, and this allows you to interact with these OpenAI models like ChatGPT or GPT 3.5, GPT-3, GPT-4, Dolly, which is a library for text to image, Whisper, which is a library to take your speech and to convert it to text, and so many other models. So first though, we will show you how we can use LM without instruction tuning. And for this, we will use a model called Bloom. So Bloom is this open source model. I don't remember exactly how big it is, but it's in the billions. So that sort of just tells you how big these models usually are. And I will show you an example of what an output is. So first, say the query that we're given is something as follows. Say the response, we're asked how are large language models made. And output you would expect is maybe something like pre-training, fine-tuning, or whatever. But when you actually run this, what you get is something like this. When you ask it how are large language models made, you get the output as how are large language models made ? Is it just a matter of having a large corpus of text, or is there some other trick to it? And this isn't what we expected, right? We wanted to answer this question. And as Dr. Willard mentioned in his lecture, the sort of what happened here is that this is just continued this sentence, right? So maybe this person thought is, well, the continuation is maybe like a book title. So the nice title here is how are large language models made ? Is it just a matter of having a large corpus of text, or is there some other trick? So that's an excellent title, but it really doesn't answer our questions. And one note that I would like to say before I move on is, in order to actually run this, you will need to have your Hugging Face key over here. So all you have to do is you go on this website, bigscience/Bloom, where we'll link the website, and then there you'll be, and there in Hugging Face, which is a very popular website where a lot of open source models are stored, and you can use it, and you can put your models on there as well. And there you get your token. You put your token right here, and then you can use that for authorization and actually running it. Now, similarly with OpenAI, you also have your OpenAI API key, which you put in here, either in your environment variable directly as os.environ OpenAI key, if you do it on Colab, or on Python, or if you're doing it on, say, Mac, you can do export OpenAI API key equals something. If you have Windows, you can do set. You can use set to get the OpenAI API key, and so you can put it in environment variables and so forth. And so you need that key for this to work, just as a heads up. So now let's think about how the same text will work if you have a model which is aligned to human values better. So has RLHF, has instruction tuning, and so forth. In this question, the question we'll ask is how are large language models made? The same as we asked Bloom, the untuned model. So let's go and run this. And this will take some time, maybe a few seconds. But after this, you'll hopefully see an output, which is a lot better than what you have with Bloom. And that's here. Great. So you have data collection. So you first collect a massive amount of textual data in formats like books, websites. Then you pre-train. So you pre-train large language models using transformer architecture. Third, you fine-tune. And fourth, you sort of repeat this process. And to really, and this is something that's really important actually, is to create a large language model that works great, that works really well, say like ChatGPT. You really need a massive amount of scale. So you'll have to, train these models on huge amounts of data and epochs and really have billions of parameters to have it work in a scale like ChatGPT. So that's how sort of we do inference on an OpenAI API on ChatGPT. And another thing I would like to mention here is I hope you appreciate with this the importance of tuning and doing things like RLHF, because this is the output you got from ChatGPT. And this is the output you get without doing any of these alignment. And there's a huge, huge difference, as you can see in the output. Okay, great. So now that we're done sort of discussing LLMs without instruction tuning and how our OpenAI chat completion works, let's talk about how we can fine tune. So the idea here is that you have your GPT-3 model and say you want to improve upon it to say work on a specific task. And for our case, in this demo, what we'll show is a sort of a question answering bot that does takes in a question about some country and answers as the country. So say you have something like which country is known for its rich history and iconic landmarks, we will output Italy. So something like that. In this case, what you can do is use OpenAI's APIs, which sort of does this fine-tuning process for you without you really having to do much. For this, the first thing you'll have to do is you will have to generate a data set for your task in Json format. And Json format is just a format that's something like this, or like a bunch of like your prompt, what a prompt is, completion, what a completion is. So completion is the output, and so forth. So it'll be in this format. And interestingly enough, actually for this example, I used ChatGPT to get this prompt, get these data. And this is actually, I think, very interesting. That a lot of, even in like research and even in some certain commercial settings, large language models are sometimes used to actually generate data to say fine tune or build upon large language models, which I think is actually quite interesting and maybe something that will be a frontier in the future. But using however means you generate a data set like this. Although I will say that if you want to use a large language model like ChatGPT to generate a data set, you probably want to do some quick quality control to make sure that the data is accurate. But if you did that, then you should be set. So this is your data set. And now you can use this OpenAI tools fine-tune the prepared data to actually prepare the data from your JSON format to something called JSON L format, which is the format they want for fine-tuning. So we will go and we'll run this. And here what do is ask us for some recommendations, and if you want to say yes or no. First, it says remove the prefix which country is from all prompts. Sure, we'll do that. Second, we will add a suffix /n to all the completions. Sounds good. Third, add a white space character to the beginning of the completion. Yeah, sure, why not? Yes, say yes. And now it says your data will be written in JSON format. Confirm. We will also say yes. Great, it did this. So now it has this country data prepared.jsonl is where it's stored. And if you actually use this cat command to sort of to see how the data looks like, it looks very similar to this, except now we had like add /n to all completion, so that's /n. We remove the prefix which country is from all the prompts. We add a white space character at the beginning of all the prompts and so forth. And this is just to help in the fine-tuning process. Now that we generated data, we use two simple things to actually get the fine-tuning working. First, we use fine-tunes like create, and we pass in our data set and the model that we want to fine-tune. So as of now, OpenAI does not support fine-tuning on ChatGPT or on GPT-4. The best you can do is GPT-3. And GPT-3 has many different models, and one such one is called ADA. So this is what we're going to be using for fine tuning. So for this, all you have to do is just run this code, fine-tune.create, found potentially. So what it says is that, so since I already ran this before, it says it found potentially duplicate file name with this. So I already started fine-tuning before. So here what it says is that, well, we can either continue the fine-tune from before, or we can just have a new one. So then for demonstration purposes, I'll just do a new one. So I'll just enter. So now it's doing its thing and it's fine-tuning. So and it'll take it takes a good amount of time depending on how big your data set is to actually fine-tune. So sometimes it takes hours to actually fine-tune this OpenAI, but when it does, it often has a lot better than GPT-3. One last thing I would like to say before heading off for questions and to talk more about the final project is that sometimes what OpenAI's fine-tuning does in particular is that it sort of cuts you off. So for that, what you'll have to do to sort of restart is do this thing called fine-tunes.follow. So what you'll do is you'll take your fine-tuning ID, which in this case is this. And once it does that, you can simply do OpenAI API fine-tunes.follow, and you can simply give the ID right over here to sort of follow and to continue the fine-tuning process. So that's all I have for this lecture. And I hope you guys learned a lot more about what large language models are, and more importantly, how we can connect a lot of the stuff we learned in our older lectures to this new frontier that you may have learned about in the news, in the media, or so forth, things like ChatGPT and all the exciting advancements in AI. And we hope that you take all of the things that you learned in this class and use it for a cause that helps better your community or your environment, and helps for social good. So thank you so much. Now I will pass it over to Shravan, who will talk a bit about the logistics of this camp, and then we can head out for questions. Shravan?
Can you guys see my screen?
Yeah, I can see it.
So there's just a few logistics things I want to go over first. So all assignments in the final project is due on the 12th of July. So 1 week from now. So even if you have some missing assignments, you can go ahead and submit them now. And then the final project will be graded and the winners will be announced 2 weeks after the final project deadline. And then you'll receive a certificate of completion for the AI camp if you submit all the assignments in the final project. And as we've received so many requests for waivers related to time zone issues, we'll not take attendance as a parameter for issuing a certificate for this camp. Do you guys have any questions about that? Here's not. Okay, finally, I'd just like to thank everybody for joining the camp. And we're so thankful for all of you that you could spend some time with us during your last few weeks. And we hope you all were able to learn a thing or two from our camp. And please feel free to keep in touch with us and keep us posted of any progress you have with the latest AI project or just something cool you found or some learning you want to share. And finally, I'd like to thank our chief advisor and mentor, Dr. Willard, without whom none of this could have happened. Thank you, Dr. Willard.
You're very welcome. And I learn a lot every time I teach this course from both you, Shreyas and Shravan, and all the students. So thank you all for being a part of this. As Shreyas and Shravan said, our goal is really to give you an introduction to these tools so that you can take this information and go out and do good for the community, the world, the environment. Thank you all for participating. We know that this is not enough for you to go land a job as a data scientist or an AI researcher. And many of you, of course, are in middle school or high school, so that's not an option anyways. But what we do hope is that this gives you some introductory tools We hope that it gives you some inspiration, so that, you know, this is something that you want to take on. It might be hard to learn the first time around, but there's plenty of good resources out there. So, you know, keep learning every day. That's something I try to remind myself all the time, even though I'm probably 2 or 3 times older than some of you. So don't stop learning, and best of luck. Are there any questions or comments from the lecture? Well, we can go ahead and end a few minutes early. If you have any questions that come up, please put them in the Google Classroom, and one of the TAs or one of us on the call will try to get a response to you as soon as we can. Thank you all.
Thank you, everyone.
Thank you. All right, thank you so much.
You're very welcome.